Okay, so this equation is basically equivalent to our Schrodinger equation. So either you solve the Schrodinger equation or this integral equation, you get the same answer. Now let's do. Now what we are interested in is the scattering solution, or the solution, our solution at very far away from the potential source. So we are assuming that here is where the potential is non-zero. It has, let's say, some size a typical size a. We would like to look for, or our detector is somewhere over here at a distance, at the position r. And a over r is much smaller than 1. So here is the potential source. We are looking at the wave function at a faraway point. Now, in this approximation, you see this r prime is basically not, it's over the all of space, but v of r prime is non-zero only in a very small region of space. So in that very small region of space, r prime is less than 8. So r prime over r is again much less than 1. R is much larger than r prime. So we can make several approximations. Here, for example, we have 1 over square root of r minus r prime. This is approximately 1 over r. And then we have the numerator. Now, in the exponent, we also have r minus r prime. Let's just expand it in this form. This is equal to r squared plus r prime squared minus 2r r prime cosine theta to the power 1/2, which is equal to r 1 plus r prime over r squared minus 2 r prime over r cosine theta to the power 1/2. Well, r prime over r is a small number in the regions which contribute to our integral. So this is approximately r times 1 minus r prime over r cosine theta plus terms of the order of, well, r prime over r squared. Those terms are ignored. So we have, this is equal to r minus r times r prime cosine theta. No, just r prime cosine theta, sorry. So what we have is e to power I p times r minus r prime. This is equal to e to power I p times r. This is our outgoing wave. E to power minus I p times r prime times cosine theta. And remember, cosine theta is the angle between our r and r prime. So if we are calculating the contribution from this r prime, this is our angle theta in the direction of our detector or our observation point. So if I define my p prime vector to be p in the r hat direction, so it's what we will be doing is, okay, so we have our plane wave coming. We will say that it has momentum p. Then it scatters from this source, and I define this p prime vector to be in the direction of my detector. So this e to power I p r minus r prime, this is approximately e to power I p r, e to power minus I p prime dot r prime. And so we have our solution at the far region. psi of r, this is equal to psi 0 of r minus m over 8 pi h bar squared e to power. Sorry, apparently I used this is k, by the way. No, this is r prime. No. Apparently I used the symbol k rather than p, so it's e to power I k r over r. This is my outgoing wave solution. D cubed r prime e to power minus I k prime dot r prime v of r prime psi of r prime. This is still an integral equation. But if v is small, or let's say even if we don't assume v is small, if this equation is correct, I can take this solution of psi and put it over here. So this is equal to psi 0 of r plus minus m over h pi h bar squared times e to power I k r over r d cubed r prime e to power minus I k prime dot r prime v of r prime psi 0 of r prime plus minus m over 8 pi h bar squared e to power I k r over r. All of this is squared. D cubed r prime d cubed r double prime e to power minus I k prime dot r prime minus I k double prime dot r double prime v of r prime v of r double prime psi of r double prime. This equation is also exact, and if you want you can just repeat this on and on. But you see this is the first term which doesn't depend on v. This is so-called of the order of v to the power 0. This first term is of the order of v. So if the potential is small, we can just keep the first term. So which will basically amount to saying that if the potential is small, the wave function will not change significantly from the psi 0. And so if it will not change significantly from psi 0 in the integral, you just put psi 0. So if this is called the firstborn approximation. Psi of r is approximately equal to psi 0 of r plus minus m over 8 pi h bar squared e to power I k r over r d cubed r prime e to power minus I k dot r k prime r prime v of r prime psi 0 of r prime. So for example, you can just for psi 0, you can choose a spherical wave of a given angular momentum ingoing wave. And then if you evaluate the integral for a spherical symmetric potential, you should get an outgoing wave and you can obtain the phase shift. Or if you put instead of psi 0, you take a plane wave, then you get this outgoing wave, which is scattered wave, and you have the scattering cross-section. So let's do an example. V of r, this is equal to V0 if r is less than, let's say, some a, and 0 if r is larger than a. Now, before we had this hard sphere potential where V0 was infinite. Now, for the hard sphere potential, this firstborn approximation doesn't work, because in this firstborn approximation, we assume that the potential doesn't change my wave function. But in the hard sphere potential, my wave function in the potential region is 0. I mean, that is a significant change from some plane wave to 0. So that's a significant change. So we cannot use it. But if you have some bump a very small bump or very small well, V0 can be both positive or negative. But if it is small relative to some other parameter in the problem, relative to the kinetic energy basically, then the first Born approximation will be good enough. And we can just choose psi0 of r to be equal to e to power I k dot r. So this will give me what f is. So I can calculate f, which is nothing but the differential cross-section. So psi of r is equal to e to power I k dot r plus minus m over 8 pi h bar squared e to power I k r over r d cubed r e to power I k minus k prime dot r prime v of r prime. So this basically tells me that f, theta, and phi, this is equal to minus m over 8 pi h bar squared d cubed r prime e to power I, let's call this q, dot r prime v of r prime. Q, this is k minus k prime. But you see that integral over there is nothing but the Fourier transform of the potential. So basically this is how we study the potential. I mean, in a given system, we don't know what the potential is. So we want to measure it. So what you do is you just measure the scattering cross-section. Now, scattering cross-section, basically you are measuring what f is. But if you know f is nothing but the Fourier transform of the potential. So you can just Fourier transform back to coordinate space, and that gives you what your potential is as a function of the position. So if you can measure, at least for small potentials, scattering basically measures the Fourier transform of the potential. So let's calculate this Fourier transform. So f is equal to minus m over 8 pi h bar squared dr r squared, r goes from 0 to a. Then we have the cosine theta. Now phi integral just brings me a factor of 2 pi and e to power I qr cosine theta v0 m over 8 pi h bar squared from 0 to a dr r squared 2 pi. Now this integral just brings e to power I qr minus e to power minus qr divided by I qr v0 well, r's cancel. We have pi cancels one of them. We have 4 minus m over 4 h bar squared. This is plus I, and we have v0 over q from minus a to a dr times r e to power I qr. This is the integral we need to evaluate. I just did the same trick as I did before. In the second, I divided my integral into 2 parts. In the second one, well, I could have just let it, in fact. Well, whatever you want to do. Then I need to evaluate this integral. Okay, let's just complete it. This is the derivative with respect to q. That brings an IR. Let me divide by 1 over I. And then I get the integral from minus a to a of e to power I qr, which is I qr over IQ r from 0 to a, minus a to a. These i's cancel. I have mv0 over 2 h bar squared 1 over q d by dq sine qa over q. etc. Okay, you can just take the derivatives. That is the differential cross-section. Is there an angular dependence here? What is Q? There is angular dependence. You see, Q, we had defined it as K minus K prime. So your particle comes in this direction and then scatters into this direction. This is our K, this is K prime. K is equal to K prime, this is equal to K. And this is our scattering angle. There's an angle theta between the two. So there is an angular dependence, although it's not explicitly seen. Well, most of the time, instead of writing in terms of the angles, you write in terms of Q. But of course, you have to convert the angles in the sigma by the omega into expressions involving Q also. So you see, d sigma by d omega is equal to d sigma by d cosine theta times d phi. This is equal to d sigma by d cosine theta. Yeah, the phi just gives me a 2 pi. It's just, in a sense, the cross-section doesn't depend on the phi. We want to calculate. Let me just keep it this way for the time being. Now let's look at k squared, or q squared. Q squared is k squared plus k prime squared minus 2k dot k prime. Well, both of these are just k squareds, so this is equal to k squared times 1 minus cosine theta. So the q squared, this is equal to minus k squared d cosine theta. Well, this minus sign basically, no, there's a factor of 2. Now this k squared basically, minus sign basically tells me that if q squared is increasing, cosine theta is decreasing. So in the definition of d sigma by d q squared, this is equal to d sigma by d cosine theta times 2k squared, absolute value. I'm not writing the absolute value. This is equal to 2k squared d sigma by d cosine theta times d phi, integrate over phi from 0 to 2 pi. Now this is my differential cross-section, 2k squared from 0 to 2 pi f squared d phi. In this example, at least, f doesn't depend on phi, so this is equal to 4 pi k squared f squared. Basically, we are done. The factor in parentheses is my f, so I take it's f squared. So this is the sigma per dq squared. Well, the nice thing about this expression is that it's also independent of how you choose your coordinate axis. Well, let's do one more example. Let's look at the Yukawa potential. So the potential we will be studying is e to the power minus mu r over R. This is the potential. Let's say V0. Now, this such a this potential is nice because it also, for example, if you have, we have this 1 over R potential for the Coulomb. That is we have this 1 over R dependence mainly because the photons are massless. So if the photon had a mass, then this would be the potential corresponding to the Coulomb law for massive photon. So let's, now to calculate F, what we need to evaluate is, well, here we have the expression. This is our F, whatever the potential is. So this is what we will be using. Just take the Fourier transform of your potential. So in calculating the cross-section, that will be the thing that you need to evaluate its Fourier transform. So the only thing we need to do is evaluate the Fourier transform of this potential. Well, let's do it. D cubed R e to power I q dot R times the potential is e to power minus mu R over R. Well, again, we can just do the angular integrations first. That will give me 2 pi from phi integral dr r squared from 0 to infinity e to power minus mu R over R. Then I have the cosine theta integral, which just brings me an e to power qr minus e to power minus iqr divided by iqr. Let me just write this as two pi times 0 to infinity. Well, the r's, they all cancel. dr e to power minus mu r. Then this is just 4 times the imaginary part of e to power iqr divided by q. Do you agree? This is equal to 4 pi over q times the imaginary part from 0 to infinity of dr e to power minus r times mu minus iq. If you evaluate that integral, imaginary part of 1 over mu minus iq, which is 4 pi over q times the imaginary part of mu plus iq divided by mu squared plus q squared. 4 pi time over mu squared plus q squared. Mu is the photon mass. Well, this model, this potential was first proposed to understand the strong force. So he said that, okay, the Yukawa, he was studying the nuclear structure. Okay, we have these protons bound together in the nuclei, but there's the electromagnetic repulsion, so there has to be some other force. So he said, let's assume that that force is mediated by some massive particle. He called it pion. He started by this argument, and then he showed that, okay, you can get this binding if the particle has a mass around 100 MeV. So that was his proposal, his hypothesis, let's say, and then we discovered the pion with masses 135 MeV. Now we have the Fourier transform. To obtain the cross-section, we have, in the definition of the F, we have all these factors, m over 8 pi h bar squared. Times this Fourier transform, 4 pi over mu squared plus q squared. All of this squared. This is our cross-section. Now, and we also had some V0 somewhere. Okay, so we started with V0. Well, let's look at the Coulomb scattering. Well, we don't need to do anything. The only thing we need to do is V0 is nothing but E squared over 4 pi epsilon 0. This is our V0. And mu is equal to 0. So the scattering cross-section is, let's see, m over 4 pi times m over h bar squared. I have 4 pi in the denominator from the overall factor. And then I have, well, hold on, what? I also have the square of this one, right? This is my f. No, okay, true. No, this is from the definition of f. So it has to be squared. D sigma over d omega is f squared. So these also cancel. Well, you see, d sigma by d omega is equal to f squared. And f is minus m over 4 pi h bar squared, the Fourier transform of our potential. So this is our Fourier transform of the potential. And there's also this overall factor in the definition of f. So let's see, what we have is m squared over h bar squared, e squared over 4 pi, or let's say alpha squared times c squared, and 1 over q to the 4, which is m squared alpha squared c squared over h bar squared. We had already evaluated what q squared was. Q squared was 2k squared, 1 minus cosine theta squared for h bar squared k squared, 1 over 1 minus cosine theta or d sigma by d omega. This is equal to m squared alpha squared c squared over 4. Well, h bar squared k squared is nothing but k to the 4. Now, let me go back. I have h to the 4, h to the 4, k to the 4. Okay, h bar squared k squared is 2me squared, 1 over 1 minus cosine theta squared. Well, m's also cancel, and we have alpha squared c squared over 16e, 1 over 1 minus cosine theta squared. Okay, one thing, there's no h bar here in the final result. But this is also the classical result. If you calculate the classical cross-section for the Coulomb potential, this is what you would obtain. Exactly the same expression. Now, another thing is, if you want to try to calculate the sigma, or total cross-section, this is equal to 2 pi alpha squared c squared over 16e squared (2 pi from the phi integral). We have the integral over cosine theta from minus 1 to 1 of 1 over 1 minus cosine theta squared, but this diverges. when cosine theta is close to 1. For the forward scattering, it diverges. Well, it basically means that, cosine theta is equal to 1 is there is no or almost no scattering. So the total cross-section corresponding to almost no scattering is very huge. Well, almost no scattering corresponds to regions very far away from your charge. But even there is some scattering for a huge area. That's basically what this divergence in the total cross-section means. It just means that this Coulomb potential reaches very far away distances. So effectively, wherever you send your particle, it will be scattered. Although very small, it will be scattered. Now, if we had this, let's say, the mu-squared dependence. Now you see, the divergence is when cosine theta is close to 1 or q is equal to 0. So when q is equal to 0, the differential cross-section diverges, and it diverges in such a way that it's not even integrable. The mass, the photon mass if the photon was massive, like the pion example, then the total cross-section will be finite. So it basically means that if you have a massive messenger, the interaction cannot go to far away distances. It is limited, and the area is limited by mu. The inverse, 1 over mu, effectively gives the size of your scattering region. Okay, for today I will stop here.
We had this firstborn approximation. There was an integral just before it.
This one.
No, you read this firstborn. The integral. We put the phi0 inside itself, right? Inside the integral. Phi.
Yes.
Then we split it up to 2 from the addition, phi0 term and the other term.
Now what we did was, okay, this is our psi, the whole expression. I took this psi and put it in this integral.
Then there was phi0 and minus some term. We split them up.
True.
But this integration depends on r prime. I'm not sure whether we did it correctly.
Let's see. Right, we didn't do it properly. In fact, what we had to do is just go back to this expression over here. You see, we cannot really do this Born, it was a mistake. We cannot really use this expression as our Born approximation. What we need to do, because this is valid only if I am very far from the potential region, but the psi I need over here is close to the potential region. So what we need to do is take this expression, so this is not correct. So this is our solution, which is exact. There is no approximation up to this point. And then we do what we had done. This is equal to psi 0 of r minus m over 8 pi h bar squared d cubed r prime e to power I k r minus r prime over r minus r prime v of r prime psi 0 of r prime. This is the Born approximation, first Born approximation. And then we have plus the other term, which is minus m over 8 pi h bar squared d cubed r prime e to power I k r minus r prime over r minus r prime v of r prime times the integral d cubed r double prime e to power I k r prime minus r double prime divided by r prime minus r double prime v of r double prime psi of r double prime. So basically, we can also have a graphical representation of this one. So we have psi, this is psi 0, it doesn't interact, plus psi 0 as my particle is propagating with a given momentum. It propagates, but there is it interacts with the potential. So this V is this V over here. What I show by these dashed lines is all these factor over here. Minus m over 8 pi h bar squared e to power I k blah blah. That factor. That is the propagator of the potential term. So kind of the potential propagates from this point to this point, and at this point it affects my particle. Plus we have the other terms. Here is my V. Now these are both the same V's. And my particle comes. There's this propagator. The potential propagates and interacts with my particle. It's this propagator over here, and then it interacts with my particle. And then there's another propagator over here. It does it again, etc. And you can, of course, increase this number as much as you want.
And the coefficient should be squared, right?
Hold on. It's squared. No, sorry, the propagator is not the propagator of the potential. The propagator is the propagator of my particle. So basically, this is my ingoing particle. There's no propagator for that. Here is my detector. It interacts first. It interacts here and then propagates to my detector. It interacts once, then it propagates to the second interaction, and then propagates to my detector, etc. It's the propagator of the particle. So you see, there is the my particle from r prime interacts with my potential at r prime and then moves to r double prime and then moves to r prime. This is my propagator. At r prime, it interacts again with my potential, and from r prime, it moves to r, which we imagine as the detector, or we are looking for the value of our wave function at the point r. And you can just generalize it. You can say that, okay, it interacts once, then another time, propagates, interacts again, propagates, interacts again, and then comes to my detector. And then we can make the approximations for each one of these terms. You see, what we are assuming is r is large, not r prime. So in this first one, I can do the approximation we did before, and so we have the outgoing spherical wave. Now in the second term, only r is large. So I can only do that in this term, on that approximation in this term. I cannot do it in this term. because r prime and r double prime both are points where the potential is non-zero. So r prime and r double prime both are small. And that is kind of what we expect, because all those terms, all these corrections should be represent at a sufficiently far away distance. They should be an outgoing spherical wave. So from this expression, we can also just directly read out the second correction to the first term. So f, the second correction to f is just minus m over 8 pi h bar squared. This whole thing squared times the integral d cubed r prime and d cubed r double prime v of r prime, v of r double prime e to the power I k dot r minus I k prime dot r k dot, no, sorry, I k dot r double prime. This is my psi 0. From this first term, we have I k prime dot r prime from this exponent when we make the approximation that r is much larger than r prime. And then we have e to the power I k r prime minus r double prime divided by r prime minus r double prime. So this is the second correction. Well, we already have the first correction to f0 plus the f1, and this is f2. Questions?
What if we measure at the points where it interacts? The probability will be infinite.
You see, in this integral, you do have terms that will be coming from when r double prime is equal to r prime. The contribution is finite. You see, in the r double prime integral, what you can do is just shift it by r prime, so that what you would have is d cubed nu r double prime divided by the length of r double prime. But d cubed r double prime, if you just write it in spherical coordinates, is just r double prime dr double prime divided by r double prime. That is finite. You see, what I mean is just make a change of variables. R double prime, let's say this is equal to r prime plus y. So if you make this change of variable, d cubed r double prime divided by r prime minus r double prime, this goes to d cubed y over y. Which is y squared dy d omega, the solid angle corresponding to this y coordinate, divided by y. So there is no divergence. So although it looks like there is a divergence, there is none really. And since you cannot really measure exactly at a given point, so you will never see that problem. Now, such divergences do arise, by the way. Not in this one, but we do have them. And what happens is we have all these tricks that we call renormalization. We just get rid of them. You will learn it later on, don't worry. You will learn it and you will not like it. But in this problem, at least everything is finite.
So like things that we cannot measure. Right?
I mean, you see, physics is about measurement, right? So if you cannot measure something, so there's no point in talking about it. So this is something that we cannot measure. It's like the infinite electric field at zero separation. We never have that.
Yeah.
Okay, so see you on Tuesday.